Hello there, students and friends. This is the last sequel of my lecture series on AC circuits. It focuses on transformers. A transformer is used to transform the voltage and current levels in an AC circuit. How does a transformer work? Find out, stick around, watch and learn. The figure shows an idealized transformer. It has two coils or windings, electrically insulated from each other but wound on the same core. The core is typically made of a material such as iron with a very large relative permeability. This keeps the magnetic field lines due to a current in one winding almost completely within the core. Hence, almost all of these field lines pass through the other winding, maximizing the mutual inductance of the two windings. The winding to which power is supplied is called the primary, and the winding from which power is delivered is called the secondary. By choosing the appropriate turns or turns ratio n sub 2 over n sub 1, we may obtain any desired secondary voltage from a given primary voltage. If N2 is greater than N1, then B sub 2 is greater than B sub 1, and we have a step-up transformer. If N2 is less than N1, then B2 is less than B1, and we have a step-down transformers. From energy considerations, the power delivered um, to the primary equals that taken out of the secondary, since there is no resistance in the windings. So we have this formula. The product B sub 1 times I sub 1 is the power average or average power in the primary, and the product B sub 2 I sub 2 is the average power in the secondary. I sub 1 and I sub 2 are the current in the primary and in the secondary respectively. If the secondary circuit is completed by a resistance big R, then the amplitude or the RMS value of the current in the secondary circuit is just I sub 2 equal to B sub 2 divided by the resistance big R. And when we combine the equations, all right, B2 over B1 equals N2 over N1, and this equation B1 times I1 equals B2 over I2, we will obtain uh, an equation, all right. After eliminating B2 and I2, we will obtain this formula, all right. B sub 1 over I sub 1 equal to big R divided by the square of the turns ratio N2 over N1. And based on this equation, we say that when the secondary circuit is completed through a resistance R, it is the same as if the source had been connected directly to a resistance equal to big R divided by the square of the turns ratio. In other words, the transformer transforms not only voltages and currents, but resistance as well. And more generally, we can regard a transformer as transforming the impedance of the network to which the secondary circuit is completed. So we now look at question number 1. Each of the following 4 transformers has 1000 turns in its primary. Rank the transformers from largest to smallest number of turns in the secondary. Letter A, a transformer that converts 220 volts AC into 12 volts AC. Letter B, a transformer that converts 110 volts AC into 220 volts AC. Letter C, a transformer that converts 240 volts AC into 12 volts AC. And letter D, a transformer that converts 220 AC into 110 volts AC. So for our solution to this question, we make use of the turns ratio formula. N sub 2 over N sub 1 equals V2 over V1. And our target variable is to determine the number of turns in secondary, or N2, using the formula N2 equals N1 times V2 over V1, starting with option letter A, or N2 is equal to 1000 turns multiplied by B2, all right, which is 12 volts, divided by B1, which is 220 volts. And we get the number of turns in the secondary equal to 55 turns. And since V2 is less than V1, all right, we classify this as step-down transformer. For option letter B, N2 is equal to 1000 turns times B2, which is 220 volts, divided by V1, which is 110 volts. So N2 will have a value of 2000 turns. And notice that V2 is greater than V1. So we call this a step-up transformer. For option letter C, N2 equals 1000 turns multiplied by V2, which is 12 volts, divided by V1, or 240 volts. The result is N2 will be equal to 50 turns. And again, since V2 is less than V1, then we classify this as step-down transformer. And finally, for option letter D, the number of turns N2 in the secondary equals 1000 turns multiplied by V2, which is 110 volts, divided by V1, which is 220 volts, and the value of N2 is 500 turns. And again, since V2 is less than V1, this is a step-down transformer. And the question is asking for the ranking of the 4 transformers in terms of their number of turns in the secondary. We are to rank them according to or from the greatest number of turns in the secondary to the smallest number of turns. So the answer is B, has the greatest value for N2, followed by transformer D, which has 500 turns, and then by transformer A, which has 55 turns, and the smallest is transformer C, which has only 50 turns. Moving on to question number 2. You plan to take your hair dryer to Tokyo, where the electrical outlets put out 110 volts instead of the 220 volts seen in the Philippines. The dryer puts out 1,600 watts at 220 volts. Question letter A. What could you do to operate your dryer via the 110 volt line in Tokyo? Question letter B. What current will your dryer draw from an outlet in Tokyo? Question letter C. What resistance will your dryer appear to have when operated at 110 volts? So our solution for question letter A, you need a step-up transformer to convert 110 volts AC to the 220 volts AC that the dryer requires. And the required turns ratio is, using the formula, N2 over N1 equals V2 over V1. That is, N2 over N1 is just equal to the ratio of 220 volts, which is V2, divided by 110 volts, which is V sub 1, and the required turns ratio is therefore equal to 2 or 2.0. So this means that the secondary coil connected to the dryer should have twice the number of turns in the primary coil, which is connected to the 110 volt line. Alright, so moving on to question letter B. What current will your dryer draw from an outlet in Tokyo? Okay, we first find the RMS current I sub 1 in the 110 volt primary using the formula average power equals product of V sub 1 I sub 1, where average P is the average power drawn from the dryer and hence the average power supplied by the 110 volt line. So the working formula for determining that current I sub 1 is just equal to average power divided by V sub 1. Substituting, we get 1,600 watts divided by 110 volts. And our answer for the current I sub 1 equals 15 amperes. Right? And moving on to our final question, which is asking for the resistance. What resistance will your dryer appear to have when operated at 110 volts? Alright? So we first list down all the data that we need. V sub 1, or the voltage in the primary, is 110 volts. The current in the primary, just calculated earlier, 15 amperes. And the turns ratio N2 over N1 equal to 2.0. Alright, so the ratio for voltage V1 over I1 is just 110 volts divided by 15 amperes, which gives us 7.3 ohms. All right? And this ratio, V sub 1 over I sub 1, okay, is just equal to the ratio of the resistance big R, all right, divided by the square of N2 over N1. And from there, we isolate the big R representing the resistance, and substituting the given, we have R, or big R equals 2.0 squared, all right? This is the turns ratio N2 over N1. You got to square it and then multiply it by the ratio of V sub 1, I sub 1, which is 2.0, or I should say 7.3. V sub 1 over I sub 1 is 7.3 ohms. And our final answer, therefore, the resistance big R is equal to 29 ohms. So that completes our answer to question number 2. Thank you very much for your indulgence. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.